For our second example, let's take a look at the area of the region bound by the curves y equals 1 over x squared, y equals x, and y equals 1/4 x. And I'll try to draw this with as much accuracy as I can here. So let's see, 1, 2, 3, 4, and 1. So y equals x, that one's easy enough, right? Small children in other countries can graph y equals x. 1/4 x, that'll go through 0, 0, and 4, 1. So let's see, we know they're going to pass through 0, 0, and you can set those two curves equal to each other to figure that out if you wanted to, but hopefully that's pretty obvious. And then we have this curve 1 over x squared, and I know what that general shape looks like. 1 over x squared kind of looks like that guy. So it's going to play across here somehow. But I want to know where they intersect. So let's find our points of intersection. So intersection points. If you wanted, you could find out where the lines intersect. X equals 1/4 x if 3/4 x equals 0 implies x equals 0, which is the point 0, 0. But we already had that visually. We also might consider where 1 over x squared and x intersect. Provided x equals 0, and it's not, we're going to have 1 is equal to x cubed, or x is equal to 1. So our first point of intersection is going to be at 1. And if we plug 1 into either one of those functions, we'll get 1. So 1, 1 is our point there. And then our last point of intersection is going to be where 1 over x squared is equal to 1/4 x, which means that 4 is going to equal x cubed, which means that x is equal to the cubed root of 4. Wherever that happens to be. So the cubed root of 4 is approximately, let's see here, 1.58, about 1.58, well, about 1.59, or about 1.6. So let's see, somewhere in here, something like that. And if x is equal to the cubed root of 4, then the y value is the cubed root of 4 over 4. Not a pretty number, but that's okay. Cubed root of 4, cubed root of 4 over 4. And our curve will come through here something like that. So that was y equals 1 over x squared. And we're interested in finding the area bound by these curves, this little roughly triangular region. Now, because all of these functions are 1-to-1, this could be done as a type 1 or a type 2. Type 1 or type 2. But since all of my curves are already kind of defined as y equals a function of x, I'm just going to go ahead and do a type 1 region. And so that's what my solution is going to look like. So I'm going to do a type 1. But in order to do that, I'm going to have to do the following. If I'm going to do a type 1 region, then I'm going to have to use vertical approximating rectangles. And if I do that, I'm going to have to break it up into two regions, area 1 and area 2, because while the bottom curve in both regions is y equals 1/4 x, the top curve that defines these regions changes. So we're going to need two integrals, and the area, which is area 1 plus area 2, is equal to, I guess I should have found this point of intersection, 1 over x squared. Oh, I already did that. So this is going to be the integral from x equals 0 to x equals 1 of the top curve x minus the bottom curve 1/4 x dx plus the integral from x equals 1 to x equals the cubed root of 4. That's leaving a bad taste in my mouth. The upper curve in that region is the 1 over x squared minus the lower curve, which is 1 over 4x dx. Yeesh. Okay, so let's clean that up a little bit. Let me see if I can make some room here, because we're probably going to need some room. For sure. Okay, something like that. Maybe I can cram this in here. This is going to be the integral from 0 to 1 of 3/4 x dx plus the integral from 1 to the cubed root of 4 of x to the negative 2 minus 1/4 x dx. Sorry to cram that in there, but I'm going to need some other room. And that's going to be equal to 3/8 x squared is the antiderivative between 0 and 1, plus the quantity negative x to the negative 1 minus 1/8 x squared between 1 and the cube root of 4. And when we begin to evaluate that, let's see, we're going to get 3/8 minus 0 plus, when we plug in the cube root of 4, we're going to get negative 1 over the cube root of 4 minus 1/8 times the cube root of 4 squared. Look, this is getting ridiculous. We're just going to start using exponents. The 4 to the 1/3 squared minus what you get when you plug in 1, which is negative 1 minus 1/8. Now, let's see if we can work a bit of algebraic magic. Everything's like 4s and 8s, so let's turn everything into powers of 2. This is 3 over 2 cubed plus, let's see, that's 1 over the cube root of 2. 4 is 2 squared, so this is 2 to the 2/3 power minus, let's see, in the top that's 4 to the 2/3 over 8, which is 2 cubed, plus 1, minus 1 over 8, which is also 2 cubed. So this is 3 over 2 cubed plus 1 over 2 to the 2/3, that's getting too small for me to see, plus 1 over 2 to the 2/3, which I'm going to multiply top and bottom by 2 to the 7/3. Why am I doing that? Because I'm clever. In the top there, that's 4 to the 2/3, which is 2 to the 4/3 over 2 cubed plus 2 cubed over 2 cubed minus 1 over 2 cubed. So this is equal to a 3 plus 2 to the 7/3, which is 2 to the 6/3 plus a third, so that's 4 times 2 to the 1/3 minus 2 times 2 to the 1/3 plus 2 cubed minus 1, all over a common denominator of 2 cubed. Heaven help me if I'm making a mistake here, right? But let's see, where are our whole numbers at? We got a 3, we got an 8, and a 1, negative 1, so that's going to be a 10 plus 4 times 2 to the 1/3 minus 2 times 2 to the 1/3 is a positive 2 times 2 to the 1/3 all over 2 cubed. We can factor out a 2 and cancel, and this will be 5 plus the cube root of 2 over 4. Yikes. I probably made a mistake there, but that looks like what that's going to be for now. Anyway, I had previously done this video, and if you're watching this again for the second time, I accidentally put a 2 there. in my upper limit, and that wasn't correct. So I had to hastily come back in here and change this video. So I hope I didn't just blast through that too fast and make a mistake, but there it is.